Всем привет, and hi everyone to my talk. It's about V8, and I know it's on the front end track, but honestly, backend developers, Node.js, also care about this a lot. But so we're going to go through the compilation pipeline in V8, and a lot of you might think, how does this help? Like how is going to know the internals of the compiler help me? It's just a tool that I use at work. But hopefully by the end of the talk, I'm going to make a case on how the internals might as well help you to write faster code and code that does not get de-optimized that often. So getting started, a little about myself. I'm Ujjwal. You can find me on Twitter or GitHub at Riserkuken. I am a co-collaborator in Node.js, just putting it out there. And I work on different projects in the JavaScript ecosystem. So one of them is V8, which is why I'm here for. I help out TC39 with some of their work, and projects like libuv, which are related to Node.js. And I'm a student. I was a student with Google Summer of Code. Not this year, but last year I was a mentor. And I'm a speaker, in case that wasn't quite obvious. But let's jump to the meat of the talk. What is V8? Like, how does V8 work? So V8, as you might know, is Google's JavaScript, or if you're fancy, ECMAScript engine. It also runs WebAssembly now, and it's used in Chromium and Node.js. Because it's used in Chromium, it's used in a lot of other browsers that are based off of Chromium, Yandex included. So yes, it has a lot of market share in the browser market, and it's pretty good. So, but yeah, the important part. Let's get this done with. How does V8 work? So you write JavaScript code, the source code, which needs to be parsed by the compiler to know what it's all about. So, but it's not parsed by the JavaScript compiler. A quick show of hands, how many people have ever used third-party code in the JavaScript applications before? Everybody? Third-party code included inside of your JavaScript bundle. And do you think you use like 100% of that code? Or like a lot of that is just junk that you're downloading on their computer? Now, it might, fun fact, it might take up to like 20 to 30% of the whole compilation pipeline in just parsing the code. So V8 does this thing where it's like, you know what, maybe they're not using all of that code. So let's see if it's immediately invoked, because that they're definitely using. And that code's eagerly parsed. Everything else is parsed lazily, so it takes less time. And it's like, if they use it, we'll parse it eagerly as well. And that parsing step results in the formation of an abstract syntax tree and scopes, which hold our variables. The abstract syntax tree is used by the interpreter to produce bytecode, which is basically Ignition is the interpreter that we use and built, and it is a stack machine. So it has like really simple bytecode that runs, but there's a problem. Interpreters are slow, right? We all know, we used to be like, oh, Python, it's slow, interpreters are slow. So I have an idea. It's actually a really path-breaking idea. Nobody had it before. Let's not be slow. Let's be fast. Let's use a compiler, but because we don't know anything about the code beforehand, let's use a just-in-time compiler. And let's use all these awesome techniques. Let's do all sorts of like state-of-the-art techniques. Yeah, don't bother trying to read any of that. But using all of these techniques, we actually make an optimizing compiler, which is called Turbofan. It takes profiling data from the bytecode which is running and optimizes the code from Ignition and produces optimized code, which may be de-optimized if the assumptions that we made using the profiling data are incorrect. So yeah, that's it. That's V8. We're done for the day. Let's go home. How do you feel about everything now? Let's take a couple steps back, because that was weird. Let's not talk about how does V8 work, but how does a compiler work? This is basically what a compiler is. It's like taking a source code and producing targeted machine code that you run on your machine. And honestly, you don't care about anything else. But like, if you look at the internals, so yeah, it has a parser which produces an abstract syntax tree. It's nothing but like a programmatic data structure that stores your code. So even if you use tabs instead of spaces, which is crazy, it has no opinions. Then it goes to the compiler, which produces an assembly program. The assembler, which takes the assembly program, produces relocatable machine code, and a linker, which produces then targeted machine code. So I guess it's simple enough now, right? Probably not. It's so yeah. It's all the compiler. Let's forget about all of this. Bad news is V8 is not this simple. But why? The question is, we can make something really simple, and we used to make something really simple, but ECMAScript is slow by default. Let's not be slow. Yeah, let's stick to the idea. But how? So I have like this really cool idea, and it's called speculative optimization. We got it. Let's all go home. It's all solved. But there's a problem. What is speculative optimization? So for the uninitiated, speculative optimization is the process of guessing what is about to happen based on what has happened. So like V8 is retrofitted with a crystal ball, and like it tries to predict the future. But yeah, that's pretty much not what it does. It makes assumption about possible future inputs based on previous inputs. So if you have a operator that is taking certain types of input, it tries to predict what kind of operands the operator will have in the future based on what you already have done in the past. Basically, it's making assumptions that we are all rational people, which we are not. But why does it help? Why does this whole speculative optimization thing even work? Like, well, why do we need it? So let's first analyze what the top 3 reasons are, in my opinion, why JavaScript functions might need optimization. Like JavaScript might be slow for a lot of reasons. In my opinion, these are the top 3. So dynamic types. JavaScript is a dynamically typed language. At this point, I guess it's not even like worth debating why that might not be the best thing for a compiler. That's a good thing for a programmer. You don't need to like care at all about the types, but the compiler has to. The second most important reason, I guess, is dynamic types, and that is the third one too. So yeah, this just does not work. We need to like at least have some character. So let's break this into 2 things. Let's have a baseline interpreter that does baseline stuff. It's like the most basic compiler, running slow stuff. And then optimize it using the optimizer compiler, as we talked about. So this is how like the whole compiler component is, as we talked. It's a baseline interpreter producing byte code, which is slow, but it has a catch. Instead of just running code, it's also collecting profiling data. Yeah, if Google wasn't already collecting enough data about you, it's also collecting data from a JavaScript source code. And now it's like, yeah, we already know so much about this person and how they write code and how they pass integers. Let's optimize it. Let's make it better for them, and that's optimized code. But these assumptions might not be true. Like it might predict that I'm going to use an int, and I might just throw a string in there. That's the de-optimization. That's why it's in red. We gotta avoid that. That's the whole point of the talk, I guess. The compiler is nothing but V8. V8 is the compiler. Ignition, that's the baseline interpreter we talked about, and Turbofan is the optimizing compiler. So yeah, this. That is great, but how does it even work, right? I mean, it's all good to talk about it, but let us consider an example. So this is a really simple code, right? You could just hack that up in minutes, and it does some really important business logic, I guess. But let's see how the abstract syntax tree for something like this actually looks like. So I'll just pop in here for a second. This is the same code that we wrote about. It's in a file called add.js. So I have a debug build of debug build running of V8, and I'll do print AST. And it prints out the abstract syntax tree. I hope everybody can see. So yeah, this helps. This is, now I know all about it. This is the most intuitive thing ever, and now I can see all of it. But no, it's hideous. So I've got it covered though. So this is something that that's close to what we had. Let's step through this. So it says there's a function at some address, which might be different based on what you're doing. It has some weird properties that nobody cares about, honestly. The name of the function is add, so that it's storing that. It's important. It has some parameters. One of the parameters is a variable x. The other parameter is a variable y. It's pretty, and it has just one statement, which is a return statement at the other address. The return statement is using the add operator, the plus operator that we use, and it's adding two things: a proxy to x and proxy to y. And once it produces all the abstract syntax tree, like it just did, it resolves the scope. It's like it goes up the tree. If it's not a parameter, it's got to be in the global scope, maybe outside somewhere. But it's like it resolves the scope. Yeah. Once this is done, we can use this data structure, because now it's not just a string, to generate bytecode. And let us step to the bytecode. So the same program, let's now, instead of printing the AST, print bytecode. Yeah. So here's the bytecode. You shouldn't care about these. This is the one that we care about. So for function add, and actually, I hope you like assembly. Yeah, it's the best language ever. So this is the bytecode that we had. And it's the generated bytecode for, as it says, function add. There are 3 parameters, but wait, we had 2 parameters. What's wrong here? Nothing's wrong. There's an implicit parameter. It's this, the receiver. Python does that explicitly. We do it like, yeah, everybody knows, everybody needs this, so just like throw it in there. Frame size is 0 because you're not defining any variables. Pretty simple. And that's the actual code of the function. Is doing absolutely nothing. Is just checking the stack because it's a stack machine, stuff that they did in the 80s or stuff. Too old. It's loading the second argument into the accumulator, because that's the only register it has. And then it adds it, right? It adds the first argument to the accumulator. But what's the 0? It could be simpler, right? No. It's not. So 2 important things are happening here. Firstly, obviously, it's adding, but is it just adding? It's complicated, right? Let's talk about that in just a bit. But the second most important thing here is, and that's what we really care about, is profiling. And the thing that you saw, 0, it's called a feedback vector. And now you know absolutely nothing about it. That's another buzzword that I threw. No, we're going to talk about it again also in a bit. But yeah, profiling, we're storing data, we're storing the type information in a feedback vector. How it works, we'll see. But yeah, it's returning whatever stored in the accumulator, so that's pretty convenient. But wait, what about the speculative optimization thing? We never did that, and now it code's running. But no, we had a feedback vector, and we stored all that information in the feedback vector. So now let's use it. Now let's optimize our code and put everything to good use. Remember the time when I told you addition in JavaScript was complicated? Yeah. So I took this from the TC39 spec for addition, and this is yeah, it's pretty simple. Just read through it, and you'll understand all of it. No, let me break it down for you. Yeah. So if you're adding 2 numbers, everything is nice. We're all going to heaven, and nothing's wrong. If you're adding strings, it's not O of 1, it's O of n, and you got to concatenate them using some weird magic. Maybe it's not O of n, it's using a rope. Oh. But if you're adding objects, then there's something wrong. Not with your code, but maybe with you. But yeah, you can add anything in JavaScript. So that's where the dynamic type thing's really biting you. But yeah, we figured this out, so we're good. How do we make that assumption? How do we assume that a person's gonna add 2 numbers or add 2 strings even? Remember the feedback vectors we talked about? Let's see how they really look to find out how it works. So that was our code. Let's add a debug print statement to it. I'll quickly go in and try to type as fast as I can. Yeah, don't try linting this. Debug print add. Yeah, and now if you do this, nothing would happen because that's not JavaScript. But if you allow native syntax, it'll print out the debug information about the function. And if you there's a lot of stuff here. It's a function and it's all the internals of the function printed out. But if you see, there's the part we care about. The feedback vector, that's the feedback vector. So yeah, this is how it looks. The feedback vector, it's nothing makes sense. Invocation count 1, that means that we call the function once. But the important point that you need to look at is the binary op. Like it says binary op signed small. So it already knows that the kind of data that you're passing through this function, it's a signed small integer. Just to see how it changes, if you do something like this, it changes into this. So it's not signed small anymore because we pass floats, and now it's a number, right? So it's kind of makes sometimes we pass values into functions that make no sense, but it's kind of trying to make some sense out of like the chaos. It's like so many values, kind of find a pattern. Because if we can, as the compiler, if we can find the pattern of how you're writing code, then we can optimize it, right? So cool. But yeah, I mean, you didn't get any of that because what the hell? Numbers, signed small, there's types in JavaScript. And what is a signed small? So yeah, is there a method to all of this? Is there like a way you could like really learn the heuristic? It's like, what's happening here? Yes. And we call that the feedback lattice. So the values in the feedback vectors, they go through a lattice, and this is it. This is the diagram that you can remember, and it'll go through you. So let's just run through this really quick. You can pass nothing into a function, which is really sad, but then the type of the function would be none. And you can pass everything to a function, which is also kind of sad though. But that makes the type of the function any. This is what you want to avoid. Go anywhere else, but avoid any. Because like then you know, it's kind of like, yeah, I don't know, just roll with it yourself, because we can't optimize it, because nothing you do ever makes sense. But there's the left part of the tree, which is like numbers or number related stuff. So there's signed small, which is really small signed integers, because apparently people use a lot of them for array indices and all that stuff. So there's a special optimized category for signed small integers. If you put in any other integers as negative integers or maybe like floats, then it becomes number. So it's not signed small anymore, but yeah, it's a number. It's big. It's stored in 64 bytes instead of 32. And there's number of or oddball. So if you throw in an oddball, like undefined or null or you know, true, false, it becomes a number or oddball. So you remember now, then somebody told you, yeah, try not to pass undefined into a function. Yeah, that's why. Because this is what it does. Like undefined kills your function. Sorry. The strings, which are stored in buffers or anything, you know, depending on the strings, and there's big integers, which are like a class of their own right now. They're not integrated into any of the existing optimizations. Hopefully they will be soon. I don't know. The data in the feedback vectors is finally used to optimize your function once the function is hot. So have you ever written hot code, like really hot code ever? Yeah. What is a hot function? So it's these nerds, man. Hot code is nothing but code that keeps running again and again and again, and it's kind of being the bottleneck. So that's the kind of code that we need to optimize, because any optimizations anywhere else other than the bottleneck are an illusion, right? So when is a function hot? A function is hot when it's slowing you down. And let us see what actually happens by explicitly triggering optimization. So this was our function, right? Let's make this hot. So yeah, let's wait for a minute. And yeah, it's done. So give me a sec because I gotta write this. Uh, So optimize on function on next call just optimizes the function on the next call, and then I console log again because I need to call it again. That's it. We're good. And if we now run it, oh no, optimize function on. Yeah, thank you. Yeah, so it's optimizing the function on the next call, but we can't see this. So we need to print out the optimized code. And yeah, that's the optimized code. Yeah, yes, 64-bit assembly. That's what we're talking about. Because yeah, it's producing really optimized code. But what did we just do? Yeah, sorry, I used to do that before. But if we use this flag, which we just did, we see the optimized code, which is something like this. And I don't understand any of that because it's weird. But let me just try to make it easy. It's just a function prologue. It's nobody cares. It's just setting up the stack and the registers and everything. And it then checks if x is a small integer, because that's the assumption we made, right? That it's small signed integers. Yeah, we checked if our assumption is correct. We checked again if our assumption is correct for y. And by this time, we're pretty sure. Yeah, we're in the optimization thing. If you see, it's like test b and j and z, which is like jump if not 0. So if by any chance the optimization failed, the assumption failed, sorry, it'll just get de-optimized, and the world will then burn and we'll all go to hell. But if we're here, it's all good, because after that it just takes the small integer, turns it into word 32, because that's what CPU's like for some reason. It turns y into a word 32 as well. It then adds both of them with an overflow check just in case it overflows and you're using pretty huge numbers even though they're small integers. And then the word 32 needs to be translated back to SMI because that's what we JavaScript developers use. So and then it just returns it and pops the stuff, like pops the stack. But yeah, let's try something fun now, right? It's been pretty boring. And what the hell is happening? So let's try something fun. We had this. Let's de-optimize. I'm kidding. De-optimization might, mean the death of your app and your career. But de-optimization is not a good thing. And by explicitly triggering de-optimization, we'll see how it actually works. But yeah, we basically use the wrong type now. So yeah, now I'll write it again. It's too slow. And instead of this, we need to trace the de-optimization to see where things went wrong. And yeah, that's what we had. See, it's pretty convenient. Let's put it on the screen. Yeah, that's the output. It's so helpful. You know exactly what's wrong. That's the best error message I had. Don't worry. So if you see here, yeah, line 2, not a SMI. That's what we were expecting, but apparently the programmer is irrational, and the thing that came is not a SMI, so it's being de-optimized now. And the SMI that was faulting was 1 plus 1.1. Actually, it's the next statement. It would be for 2.2, but yeah, it's already de-optimized at this point. So that's the pro tip. If you don't want your code to be slow, try to stick to certain types. It makes things easier, and everybody's happy. So that's most of it. I wanted to just give a shout out and thanks to Benedict Moorer at Beamer. He's a great guy, works at Google, as do all the other people. Yang Guo, Satya, Jacob, Sigurd. Everybody's been great help for this talk as well as my work, and the organizers. You guys are awesome. And thank you all. The Sasiba and.
Давай я дойду.
Hey, thanks for the great talk. I'm just curious, why like you don't make the totally typed version of V8? Like not you specifically, but the team. I mean, it's a huge pain to embrace the untyped JavaScript nowadays, and like as you know, the world is shifting towards TypeScript and Flow, etc. So it makes no sense to make it for the browser because, well, it will ruin the web. But for the server,
I mean, yes, you got to talk to TC39, make a new language, which has a better type system. But I guess like one of the reasons JavaScript is stuck at dynamic type is because that's like that was the USP starting out. Like, yeah, we're dynamically typed. It's easier to code. Everything is simple. And another thing is it's actually you said a thing. It's like it makes no sense for the web, and I do not like 100% agree with this. Sometimes dynamic types make a lot of sense on the web because like the front end web, in my opinion, is like the most dynamic place because like you working with all sorts of stuff and everything's happening in real time, unlike a lot of back end code where you're in a sandboxed closed environment. It's like, yay, it's all happy, but like front end for me is like the wild wild west, and people can be doing anything, and your libraries could be like all over the place. And it's like, yeah, maybe why not leave it up to the developer to see if they want like. So this is the idea. This is monomorphism, which is something we are imposing on ourselves. So if you use V8, if your users are using V8, running your code on V8, and if you stick to a single type, if you impose it yourself, then it's going to be optimized. So, but if you do not want, if for some reason you want to pass like objects of all sorts of shape to a single function, then yeah, that's also something that it allows you to do. So it's like really permissive, and it's like, yeah, do whatever you want, play with it.
Поднимайте руки. Okay.
Hello, thank you again for this presentation. We had a good look at the internals, and you probably have a great perspective on this, being a member of TC39. What do you think is the current state of V8 optimizations relating to the maximum mathematically possible optimizations on the current JS as it is? Like without types, without any special tricks, like is V8 already at the maximum capacity? And that's the first part of the question. And the second part of the question, there was a proposal about optional typing in JavaScript. Do you think it's going to come through? And do you think it's going to help with optimization in this field?
Thank you for the question. By the way, I'm not a member of TC. I just help out. I'm not a voting member, sitting on meetings and stuff. But yeah, it's so V8 is like, the way I look at it is V8 is like Google when they launched V8. It was Google saying, you know what, modern web applications just don't work with slow JavaScript compilers. And it's like, if you're not going to make a fast JavaScript compiler, we are. And eventually everybody just adopted the techniques that the V8 team started out, and it's like it's shaming the world into making better JavaScript compilers. Like these days, all major JavaScript compilers use state-of-the-art tools, or they start using Chromium, Edge. But yeah, I mean, it's pretty fast originally, and the V8 team tries to push it to the limits as much as we can. But I'd say like if you consider like purely dynamic typing, no fancy tricks, it's as fast as it gets. The problem is the spec itself is slow. So as I showed you, the thing for the addition, it's like you gotta check if it's a primitive, you'd like to convert it to objects and stuff. And it's like, that's the stuff that's slowing us down. This JavaScript spec makes JavaScript slow. And what these fancy tricks V8 does is essentially skipping a part of the spec. It's like, you know what, I can just assume that JavaScript was statically typed and could still make it work. So yeah, I hope that answered your question.
About optional typing, do you think it's anywhere on the list of the future implementation?
Optional typing is that's a lot of work for compiler vendors and people. And as I said, like you could impose things like this on yourself. You could use some tooling for type checking, and you could do like not 100% maybe, but like to a lot of extent, you could actually do type checking yourself. So why the thing my opinion on this is, if you put something like that into the language, because JavaScript is a standards-based language, it's never going out. So we're stuck with that. And I'm like, are we sure that it's the best possible option? If yes, then maybe sure. But as long as we're not like 100% sure, adding it to the JavaScript standard would mean it's there forever.
Thank you.
Thank you for great speech. My question is about linker.
Okay.
So basically, I suppose that the problem could possibly be solved by having, for example, two functions. One is optimized and one is not, just to avoid the optimization phase. And like, for example, we have ad hoc polymorphism in, for example, C++ linker, and there is possibility to create different functions. And one function we can use for example, integers, and some de-optimized version for any other types. Mm-hmm. So is there any work on improving the linker itself, how linker works?
Yes, I mean, thank you for the question. There's a lot of these you know, I wouldn't call them tricks. A lot of these optimization techniques being discussed every day at not just at V8, but also like SpiderMonkey, and everybody cares about them, and all these nerds are reading all the research papers in compilers technology. It's just that it's a lot of work to actually commit to a single technique. So I guess it's more like, so we saw the whole diagram of Turbofan with like inlining and you know, doing all sorts of stuff, the sea of nodes graph and all these techniques. I guess it's just about, you know, which 20% of the techniques, I'd say, make 80% of the performance difference. And I guess the sea of nodes graph was one of those things, for example, and maybe some other technique is not. That does not mean it does not make your code faster. Maybe, you know, it's just a lot of work to maintain, or maybe it's just a lot of work to implement and it's not being implemented yet. So yes, definitely, any viable optimization technique that can be used in V8 will hopefully one day be used with all these awesome people working on it. But yeah, thanks.
Hello, thank you for a great talk. My name is Andrei, and I'm curious. You show us a very big picture of internals of V8, and can you point thing where WebAssembly is in that picture? Yes.
So I didn't include that flow into the diagram because I was like, yeah, we're going to talk about JavaScript only. But yes, so there's the compilers we talked about, right? This the ignition interpreter, and there's Turbofan. And so the compiler that we use for compiling WebAssembly, it's called Liftoff. And it's really cool. It has like rocket ship in its logo. How cool is that? But yeah, it's called Liftoff, and it's actually right after parsing, and it's the actual compilation pipeline, the box that we discussed, which said compiler. Yeah, that one's, instead of ignition and Turbofan, it's Liftoff, because you don't need to like just-in-time compile WebAssembly. It's perfect as it is. But yes, that's the alternate pipeline, and it's a lot of people have been working on it. It's definitely improving for the better, But hopefully in the next few years, we'll see a lot of great WebAssembly stuff on V8.
Okay, so it has a separate compiler,
Yes.
but bytecode is running on the same virtual machine than JavaScript, or separate.
WebAssembly, I don't think, so I'm not qualified to talk about this, but I don't think WebAssembly needs to be run on a virtual machine. It can just run on a computer.
Thank you.
I mean,
I
like,
get.
after it passes through liftoff. Yeah. Right.
So let's suppose we have this beautiful add function, and in our code, half of the time we call it with small integer, and half of the time we call it with float. Those pipeline will create two optimized versions and switch between them, or it will de-optimize and optimize all the time.
Yes. Thanks for the question. That's a really good observation that we can maybe store the two optimized versions and switch between them. So there's a few problems with that. Firstly, you don't know ahead of time how many optimized versions you need. So people, so all this speculative optimization stuff, people go crazy after projects like Electron and Chrome itself. Obviously, it's like, oh, so much RAM is going like to waste. I'm like, that is why it's not being wasted. It's being used to do really awesome stuff, and that is why it's a really fast browser, because it's using your RAM for really ingenious stuff. But yeah, so if you have like twice the amount of optimized functions stored, then that's like also going to be, and then it's also going to be a bit complicated, because like to actually make that assumption that a person is like parameter A, parameter B, and swapping between them, it's like, I don't think a lot of people do something like that. A lot of people just like either go one way, which is the nice way, and they go all the ways, which is like the path of the any. But I would say that the sled, we call it the sled, is like where you determine which optimization to use. It itself will make the code so slow. It's like, okay, if it's a SMI, then go here. If it's a float, then go here. It's like so many types. Why not just use the de-optimized function? Like after 3 or 4, I think it'll get to the point. It's like, just use the de-optimized function. It's just as fast. So yeah, thank you.
Hello.
Hi.
Thanks for your talk. Could you show us some more practical examples which code will be optimized and which code will be de-optimized?
Yes. Let's not bore everybody with this, and you could meet me in the discussion zone, or if anybody else wants, I'd be in the discussion zone and in the speaker area and just hang around the conference.
Okay.
So yeah. But yeah, like this is what actually prompted me to give this talk. When I started working on V8, Node.js like, yeah, could you be the guy who talks to the kids who need to know about V8? And a lot of people would like make issues on the Node.js bug tracker, and they would be like, oh, these two codes are these two like programs in JavaScript are exactly the same. They're doing the exact same thing. They're just written a little bit differently, and this one takes 10 times the amount of time this one does. And I'm like, yeah, that's why. And this is like the whole point of the talk. It's perfectly fine if you're that person, because yeah, why the hell do you care how much time V8 is taking? But to help you formulate a basic set of heuristics and ideas, like, yeah, maybe this is why the code is not as fast as it should have been, and it'll be really cool for everyone, I guess, if the next time you do a code review, you're like, hey, you see this thing over here? It's making our code slow. Let's improve that.